Hey everyone, and welcome. Today, we're going to pull back the curtain on the invisible engine that, no joke, powers basically our entire world. It's a device that's so common we don't even see it anymore, but once you understand its simple, elegant trick, well, you start to see it everywhere.
So let me just start with a question for you. What do you think is the single most important invention that you interact with every single day, but have probably never, ever given a second thought to? Nope, it's not your phone, not the internet. It's something way more fundamental.
You guessed it, it's the humble induction motor. Seriously, from the fan that's cooling your room, the pump that brings water to your tap, all the way up to the giant machines and factories that build our cars, these motors are absolutely everywhere. They are the quiet, unbelievably reliable workhorses of modern life. Okay, so let's get properly introduced to this invisible workhorse. We'll start with the basics, and then we're going to tackle the central puzzle that makes this whole thing seem kind of like magic. So what even is an induction motor? Well, it's a type of AC electric motor, but it has this one very special trick up its sleeve. You see the spinning part, right? That's called the rotor. And here's the thing. There are no brushes, no wires, no direct electrical connections touching it at all. The current that makes it turn is created wirelessly through something called induction. And because there are no parts to wear out, they are just incredibly simple and reliable. And that right there brings us to the core mystery. How on earth does the rotor spin if you aren't feeding it electricity with wires, right? There are no contacts, it just spins. It really does feel impossible, like some kind of magic trick. But you know what? It's not magic. It's just really, really cool physics. To solve this little puzzle, we have to look at the physics behind it. And it all boils down to one fundamental force of nature, a totally invisible push that makes this entire invention possible. That force is called the Lorentz force. This is the secret ingredient to everything. All it means is that when you have a moving electric charge, a current, and you put it in a magnetic field, the field actually exerts a force on it. It's this beautiful little dance between electricity and magnetism that the motor is built on. And look, if you remember one thing, remember this. A magnetic field literally pushes a moving electric current. That's it. That's the whole game. The motor is just a machine that's cleverly designed to harness this one fundamental push. And what's really cool is we can even figure out which way that push is going to go, using something called the right-hand rule. You can try it right now. If you point your index finger in the direction the current is flowing, and your middle finger in the direction of the magnetic field, your thumb will point in the exact direction of the force. It's a neat little trick to visualize what's happening. All right, so we've got our invisible push. Now, let's see how some brilliant engineers managed to harness this. This is where we go from a cool physics concept to an amazing piece of engineering I like to call the Great Magnetic Chase. Okay, so step one happens in the stationary part of the motor, which is called the stator. By pumping alternating current through coils of wire, all timed perfectly, it creates a magnetic field that doesn't just turn on and off, it actually spins around in a circle. It's like a perfectly controlled magnetic whirlwind. Now, sitting right in the middle of this magnetic whirlwind is our rotor, which is really just a simple cage made of metal bars. As that spinning magnetic field sweeps past the rotor's bars, guess what? It creates an electric current in them. Wirelessly. It's the exact same principle that makes a transformer work. And right here, this is where it all comes together. We now have our two key ingredients, right? We have a magnetic field, and we have an electric current sitting right inside it. So that rotating magnetic field immediately starts pushing on the very current that it just created in the rotor. And that constant push creates torque, a twisting force. The rotor has no choice but to start spinning, trying to catch up to the rotating magnetic field that's basically dragging it along. It's like a mechanical dog chasing a magnetic rabbit that it can never, ever quite catch. And that endless chase is what makes the motor turn. But here's the really clever part. The rotor never fully catches up. There's always a tiny difference in speed, and that's called slip. And you actually need the slip. Think about it. If the rotor ever spun at the exact same speed as the field, the magnetic field wouldn't be sweeping past the bars anymore. And if that happens, no current is created, and the Lorentz force just disappears. The motor needs that chase to keep on going.
So now that we've kind of demystified the magic, let's zoom out and look at the history of this thing and the just enormous impact it's had on our world.
So the story really gets going in the late 1880s. A guy named Galileo Ferraris and, of course, the legendary Nikola Tesla both independently figured out how to make that smooth, rotating field we talked about. Westinghouse licensed Tesla's patents, and then the real game changer was when they and GE agreed to share the design for the super simple and rugged squirrel cage rotor. After that, the technology just exploded. And this number just perfectly illustrates the progress we've made. A modern 100 horsepower induction motor is the exact same physical size as a 7.5 horsepower motor was back in 1897. That is more than 13 times the power in the same footprint. It's an incredible leap, all thanks to better materials, better insulation, and a whole lot of smart design. Now, of course, no machine is 100% perfect. You're always going to lose some energy. In these motors, you lose a little bit of heat from electrical resistance in the copper windings. Some energy is lost just magnetizing the iron parts. And then, of course, you have basic stuff like friction. And engineers are in this constant battle to try and shave down every single one of these little losses. I think this quote from the engineer Philip Auger just sums it up perfectly. He said, "An induction motor is basically just a transformer where the second coil is allowed to spin." It's such a simple, elegant, and powerful idea. So, next time you hear that quiet, steady hum coming from a fan or an elevator or maybe even a train pulling out of a station, you'll know what's happening. It's the sound of an invisible chase between magnetism and electricity. It's the sound of the Lorentz force tirelessly pushing our entire world forward.